In March 1945, the war in Europe had entered its final and most decisive stage. The Allied armies, advancing relentlessly from the west, had reached the banks of the Rhine River, the last and greatest natural barrier before the heart of Germany. The Rhine stretched like a silver wall across the continent, almost 1,300 kilometers long, cutting through mountains, plains, and industrial valleys. For centuries it had been both a lifeline and a line of defense. Now, in the last months of the war, it became the final obstacle separating the Western Allies from the swift collapse of the Third Reich. The German command knew its value. As their armies retreated, they carried out a systematic demolition of every major bridge from the Swiss border to the North Sea. Concrete arches that had stood for generations were blown apart by explosive charges. Railway viaducts fell into the water with a roar that echoed across valleys already filled with smoke. By the time American and British forces reached the West Bank, nearly every permanent crossing was gone. What remained were fragments, twisted steel beams and skeletal piers jutting out from the floodwaters. For the Allied soldiers who arrived in late February and early March, the Rhine was not just a river. It was a psychological frontier, wide, fast, unpredictable, and under constant watch by German artillery. Reconnaissance reports described the current as treacherous, swollen by melting snow and early spring rains. The water carried broken barges, uprooted trees, and the remnants of destroyed towns. Any attempt to cross it required perfect coordination between engineers, infantry, and air support. The city of Wesel, located on the lower Rhine near the Dutch border, became the focal point of this challenge. Once a medieval trading port, it had been almost completely leveled by Allied bombers to deny the Germans a defensive stronghold. By the time ground forces arrived, the town was a wasteland of craters and shattered walls. Yet its location, where the river was broad but relatively calm, made it the ideal point for a large-scale crossing. From here, the 9th U.S. Army planned to launch Operation Plunder, the massive push that would bring Allied forces onto the eastern bank and open the way to the Ruhr. On the west bank, thousands of soldiers and vehicles crowded the muddy roads leading to the water. Artillery batteries lined the hills, firing across the river to suppress German defenses. Behind them stretched a logistical sea of fuel trucks, ambulances, and supply convoys. Engineers unloaded pontoon sections, steel beams, and treadway panels, stacking them in precise rows under camouflage nets. The air was filled with the low hum of generators and the rumble of amphibious craft being tested in the backwaters. For weeks, preparation had been underway, surveying the riverbed, calculating currents, training men to assemble bridges in record time. Every movement had to be rehearsed, every piece of equipment checked twice. On the far side, German units of the 1st Parachute Army waited in trenches and cellars, determined to hold the line at any cost. Their orders were simple: deny the Allies a bridgehead. To the civilians still trapped in villages along the eastern bank, the Rhine became both a barrier and a prison. Flooded fields and destroyed ferries left them isolated, living in basements and barns as artillery shells passed overhead. Many of them watched the western shore at night, where hundreds of small fires burned, signals of the vast army preparing to cross. By mid-March, the weather turned colder. The river's surface reflected the orange glow of burning towns and the distant flashes of anti-aircraft guns. In the morning mist, engineers could see the outlines of the far shore only for a few seconds at a time. The scale of the task before them was staggering. To bridge the Rhine meant to overcome not just distance but chaos, the force of the current, the threat of German fire, and the weight of history itself. Every man understood that what they were about to attempt would decide how quickly the war would end, and how many would live to see it. The Rhine had stopped invaders for centuries, Romans, French, and Prussians alike. But in March 1945, it would be crossed once more, not by conquest but by engineering and coordination on an unprecedented scale. The challenge that lay ahead was not only to fight, but to build, to connect two worlds separated by destruction, and to carry an entire army across a river that refused to be tamed. The sector near the German city of Wesel posed one of the most formidable engineering challenges of the entire Western campaign. Operation Plunder, The Allied plan to force the Rhine and establish a bridgehead on its eastern bank depended entirely on the ability of the engineers to construct stable crossings under fire and against the force of nature itself. The Rhine at Wesel was broad and restless, swollen by weeks of rain and snow melt from the distant Alps. Its current was swift, carrying silt and debris that made any construction perilous. What had once been farmland on both sides of the river had turned into a sucking plain of mud. Roads ended abruptly at flooded fields, and every attempt to move heavy equipment toward the water risked vehicles sinking to their axles. For the American Ninth Army, Wesel was the key to unlocking the final phase of the campaign in the Ruhr. The terrain offered no alternatives. Upstream crossings were narrower but heavily fortified, and downstream sections were dominated by bogs and destroyed canals. The only viable route lay through the ruins of Wesel itself. Yet the devastation that made the town indefensible also made it almost unusable for logistics. Bombing raids in February had reduced the infrastructure to rubble. What remained of the riverfront was a jagged wasteland of broken docks, shattered cranes, and the wreckage of ferries. The banks had eroded into steep, unstable slopes, constantly collapsing under the pressure of the current. German forces had prepared for months to make the Rhine a death trap. Demolition teams mined the approaches to the river and rigged artillery zero points along the far bank. Observers in camouflaged positions waited to call down counterfire on any sign of construction. The air above the river was under constant surveillance by both sides, Allied reconnaissance planes circling high above, and German anti-aircraft guns hidden among the ruins. Every attempt to launch even a small reconnaissance boat risked being met with shellfire. The engineers knew that when work began, they would be fully exposed on open ground, dependent only on timing and smoke screens for protection. The physical conditions were equally punishing. The Rhine at this point was nearly 400 meters wide, its surface rippling with eddies that could overturn pontoon sections before they were linked. Each steel Treadway pontoon weighed over a ton and required precise alignment to interlock with its neighbors. Any miscalculation in angle or speed could send an entire section drifting downstream, where the current would twist and crush it against the next span. Anchoring was a nightmare. Standard cable lengths proved too short to hold the heavy pontoons against the flood. Engineers had to improvise by using doubled anchor chains and reinforced winches scavenged from amphibious vehicles. Even before construction could begin, the staging area had to be stabilized. The west bank was a mire of soft earth and bomb craters, where bulldozers sank with every movement. Trucks delivering Treadway panels stalled repeatedly, forcing men to drag the steel pieces forward by hand. In some sectors, engineers laid entire carpets of planks and sandbags just to create a path to the water's edge. The mud swallowed tools, flooded foxholes, and clung to uniforms until men could hardly lift their legs. Yet the timetable of Operation Plunder allowed no delays. Each hour lost meant that infantry waiting behind the line remained exposed to counterattack, and artillery batteries were forced to fire longer than planned, risking ammunition shortages. To make matters worse, weather reports predicted another storm front moving in from the North Sea. Rising winds threatened to make the river even more dangerous. If the crossing was delayed, the operation would have to be postponed for weeks, a political and strategic disaster when every day counted. Supplies of fuel and food had already been redirected toward the assault. There was no room in the schedule for failure. Commanders pressed for updates every hour, aware that a single breach in planning could stall the entire Allied advance. The engineers faced a dilemma that went beyond mechanics. They had to build a bridge strong enough to carry tanks and convoys, yet flexible enough to float with the river's motion. It had to be assembled in total darkness under enemy fire, and it had to hold from the first moment men set foot on it. Any collapse would not only kill those crossing but could demoralize the entire army waiting on the shore. The stakes were absolute. Behind them, rows of field hospitals were filling with wounded from preliminary raids. Evacuation boats needed a reliable crossing to move casualties to safety on the western side. Every delay meant more soldiers dying before reaching medical aid. For the engineers of the Ninth Army, the mission at Wesel became more than a tactical objective. It was a race against time, water, and exhaustion. The Rhine stood before them as a living wall, indifferent to human effort, and yet it had to be mastered. The success of the entire campaign, and perhaps the speed at which the war in Europe would finally end, rested on their ability to solve that one problem, to bridge the unbridgeable. By the spring of 1945, the United States Army Corps of Engineers had become one of the most experienced and technically capable forces of its kind in military history. 3 years of continuous operations across multiple theaters had transformed the engineers from support troops into the silent architects of victory. From the beaches of North Africa to the mountains of Italy and the flooded plains of northern France, they had learned to build under fire, to improvise with what they had, and to turn destruction itself into raw material for construction. Every bridge, road, and airfield built since 1942 carried the marks of their evolving expertise. The Bailey Bridge, developed by the British and adopted widely by American forces, became their most versatile tool. Lightweight, modular, and assembled without cranes, it allowed engineers to replace a destroyed bridge in a matter of hours. Thousands of Bailey spans had already been laid across Europe, carrying tanks, trucks, and ambulances from Normandy to the German border. The system's adaptability had saved entire offensives from collapse. Yet, as effective as it was on smaller rivers like the Seine or the Meuse, it was not suited for the vast, fast-flowing Rhine. The river's width, reaching more than 350 meters in places, demanded floating structures capable of supporting heavy armor while flexing with the current. The answer lay in the pontoon Treadway Bridge, a floating structure composed of steel pontoons linked together with interlocking treadways. It was a marvel of wartime engineering, designed to be deployed rapidly from amphibious trucks and assembled directly on the water. Each pontoon could carry up to 20 tons, and when joined in sequence, they formed a continuous path capable of supporting tanks such as the M4 Sherman and M26 Pershing. American engineers had perfected its use during earlier campaigns. In Italy, they had spanned mountain rivers under enemy artillery. In France, they had bridged flooded valleys where permanent roads were impossible. Every crossing refined their methods, quicker anchor systems, better night assembly procedures, and new smoke deployment tactics to mask construction from observation. By late 1944, as the Allies advanced toward the German frontier, bridging became the most critical logistical task of the war. The speed of armored divisions depended entirely on the engineers' ability to repair or replace crossings destroyed by retreating German forces. The Corps of Engineers developed mobile bridging battalions, highly trained units that could deploy within minutes, equipped with prefabricated panels, heavy winches, and amphibious vehicles known as dukas. Their unofficial motto, often painted on the sides of their trucks, was, "First in, last out." Wherever an army moved, engineers went ahead to make the impossible possible. The Rhine, however, represented an entirely new challenge. It was the widest, deepest, and most strategically important river in Western Europe. Its current was unpredictable, its banks steep and unstable, and its eastern side bristled with defenses. German planners had long considered it a natural fortress. They mined the approaches, destroyed infrastructure, and placed artillery batteries to cover every likely crossing point. Earlier in March, at Remagen, American forces had captured the Ludendorff Bridge intact, a stroke of luck that gave the Allies a brief foothold east of the river. But that bridge was the exception, not the rule. Everywhere else, engineers would have to build their own connections under hostile fire and impossible conditions. The success at Remagen had shown that crossing the Rhine was achievable, but it also exposed how fragile such victories could be. Within days, the Ludendorff Bridge collapsed under structural stress and repeated German air attacks. For the planners of Operation Plunder, that collapse was a warning. A temporary or unstable crossing could endanger an entire army. The new bridges to be built near Wesel would have to carry not just infantry but thousands of tons of tanks, fuel, and supplies each day, and they would have to remain operational for weeks. No margin for error existed. By this point, the Corps of Engineers operated with the precision of an industrial enterprise. Each company specialized in different components, anchor teams, assembly units, and transport detachments, moving in perfect sequence. Their equipment was standardized, their routines rehearsed countless times in field exercises. Yet despite all their experience, no previous river demanded so much coordination, endurance, and courage. The Rhine was not simply a geographic obstacle. It was the last barrier between the Allies and the heart of Germany. To bridge it meant more than building a structure, it meant breaking the symbolic boundary of the Third Reich itself. The crossing at Wesel would therefore test every lesson the engineers had learned since Normandy. It required innovation, endurance, and calm precision under direct enemy observation. What they were about to attempt had never been done before on such a scale, constructing the longest floating Treadway bridge ever built in combat, in the midst of one of the largest coordinated assaults of the Second World War. For the men of the U.S. Army engineers, the Rhine was not just another river, it was the culmination of their craft, the moment when engineering became as decisive as any weapon on the battlefield. At dawn on March 24, 1945, the gray mist over the lower Rhine thickened with the smoke of hundreds of artillery guns. It was the opening act of Operation Plunder, the largest coordinated river crossing of the Second World War. The thunder of Allied bombardment rolled without pause, aimed at silencing German batteries on the far bank. Under that deafening cover, the engineers of the U.S. Ninth Army began their most dangerous task, building the bridge that would carry an entire army across the Rhine. The night before, the 17th Airborne Division had already dropped behind enemy lines as part of Operation Varsity, seizing key roads and disrupting communications. That airborne assault, though critical, also raised the stakes for the engineers. The paratroopers needed reinforcement and resupply as quickly as possible, and every hour the bridge remained unfinished risked isolating them. The engineers knew their work was not simply construction, it was the spine of the entire offensive. Without their bridge, the crossing would be fragmented, and the success of both operations would hang in the balance. As the first light broke, platoons from the 17th Armored Engineer Battalion and the 82nd Engineer Combat Battalion moved toward the water. They wore dark uniforms smeared with mud and oil to blend into the riverbank. Trucks and amphibious ducks crept through the fog, carrying the massive Treadway pontoons that would become the floating foundation of the bridge. Each section was made of heavy-gauge steel and weighed more than a ton, requiring coordinated effort just to move it into position. Teams of 6 to 8 men guided the pontoons down wooden ramps coated in grease, sliding them into the river where the current immediately seized them. Every movement had to be synchronized. The men used steel cables and winches anchored to the shore to control the floating sections, hauling them into alignment against the pull of the current. The Rhine was restless that morning, swollen from spring runoff and littered with debris from destroyed buildings upstream. Logs, barrels, and fragments of bridges drifted downstream like silent hazards. The engineers worked knee-deep in icy water, hammering bolts and locking Treadway panels into place, while the sound of artillery fire reverberated across the valley. Above them, the sky flickered with the flashes of anti-aircraft guns as Allied bombers continued their bombardment of the opposite bank. Communication along the riverbank was nearly impossible. The noise drowned out shouted commands, and smoke obscured visibility beyond a few meters. Engineers relied on hand signals and instinct honed through months of training. The process was mechanical but demanded precision: align, pin, lock, tighten, anchor. Any deviation in angle or timing could twist a pontoon, opening a gap that would spread down the entire span. The men learned to read the rhythm of the current, waiting for brief lulls before connecting sections, driving home bolts with frozen hands. Despite the bombardment, German resistance was fierce. Mortar fire occasionally bracketed the river, sending plumes of water into the air. Machine gun bursts rattled from the far bank, searching for movement among the smoke. The engineers kept working. When a shell struck nearby and drenched a section in spray, the men paused only long enough to recheck the cables. Their discipline under fire reflected the ethos of the Corps of Engineers: precision before panic, structure before safety. By midday, the outlines of the bridge began to emerge from the fog, a dark chain of steel pontoons stretching into the current. Cranes mounted on amphibious trucks swung sections into place, while crews tightened bolts and laid the continuous Treadway. The surface gleamed with water and oil, but it held firm. Officers walked the length of the growing structure, inspecting each joint and signaling for adjustments. To keep the pontoon stable, teams installed heavy anchor cables, attaching them to concrete blocks buried deep in the west bank. The cables sang under tension, vibrating like piano strings as the river pulled at them. On the eastern shore, the German positions still fired sporadically, but their effectiveness waned as Allied smoke screens thickened. By afternoon, the first test vehicles were lined up, jeeps, then light trucks, then tanks. Among them were M4 Shermans and M26 Pershings, their engines idling as crews watched the engineers secure the final panels. When the order came to move, the tanks advanced slowly, treads clanking against the metal decking. The entire bridge flexed under the weight but held. The engineers stood silently on the shore, watching the first vehicles cross into Germany proper. That moment, when the first tank reached the far bank, marked more than the success of a construction project. It was the fulfillment of months of preparation and the culmination of years of hard-earned knowledge. In less than a single day, under constant fire and in brutal conditions, the engineers of the Ninth Army had accomplished what centuries of armies before them had failed to do. They had bridged the Rhine by force. The crossing at Wesel had begun, and with it, the final march into the heart of the Third Reich. The construction of the Treadway Bridge at Wesel unfolded with the precision of an industrial operation, executed under conditions that no factory could ever simulate. Once the first pontoons were secured to the west bank, the engineers moved into a relentless rhythm that would continue without pause for the next 9 hours. Worklights mounted on amphibious trucks cut through the smoke and fog, illuminating the water in narrow beams. Every platoon had a designated task: launching, alignment, anchoring, decking, and inspection, and each task was performed with near mechanical timing. It was the culmination of years of training, condensed into a single day of chaos, noise, and discipline. The 17th Armored Engineer Battalion led the effort on the main Treadway span, while the 82nd Engineer Combat Battalion managed supplementary floating bridges and ferries. Equipment convoys arrived continuously from the rear, carrying pontoon sections, anchor chains, and heavy decking panels. The pontoon units, known as M2 Treadway Bridge Equipment, consisted of rectangular steel floats designed to interlock with hinged treadway panels that formed the bridge's driving surface. Each float was launched from amphibious dukas or pontoon trucks, guided into position by men on small assault boats. The current fought every movement, tugging at the sections as if to tear them apart, but the engineers countered it with a system of mooring lines and tension winches secured to the banks. Progress depended on absolute synchronization. As one crew bolted treadway sections together, another reinforced the anchors and adjusted the spacing between pontoons to balance buoyancy and flow. The engineers had to calculate the precise load distribution for tanks weighing up to 35 tons, ensuring the bridge would neither sag nor buckle under pressure. They used steel crossbeams and hinged locks to distribute weight evenly, creating a flexible but resilient surface. Each completed segment was tested immediately by light vehicles before the next section was added. To stabilize the entire structure, the crews installed a network of anchor lines that crossed beneath the water in a lattice pattern. These were attached to massive concrete blocks and steel pickets buried deep into the western bank and supplemented by additional anchors on the far side as soon as the first teams reached it. The alignment of these anchors was critical. Even a few degrees off could create torsion strong enough to twist the bridge apart. Engineers constantly monitored the tension of each line, adjusting the winches to compensate for the fluctuating current and the weight of vehicles already crossing. The assembly of the decking was the most delicate part of the process. Each steel treadway panel was fitted onto the pontoons and locked into position with precision bolts. The panels formed 2 parallel lanes for vehicles, with wooden planks laid between them to serve as walkways for personnel. Soldiers worked bent over the cold metal, tightening bolts and checking for warping caused by temperature differences. Every hour, officers inspected the joints with flashlights, ensuring the sections remained watertight and aligned. The noise of hammers, engines, and chain winches created a metallic rhythm that echoed across the river, blending with the distant artillery fire. As the span grew, logistical coordination became as vital as physical labor. Supply trucks rotated constantly between the assembly sites and the depots farther inland, delivering spare parts, replacement pontoons, and fuel for the amphibious vehicles. When one of the trucks became stuck in the mud, engineers immediately used bulldozers to drag it clear, unwilling to lose even a few minutes. In the background, signal units maintained constant communication with artillery command, timing their smoke barrages to cover the most exposed stages of the work. It was a carefully choreographed partnership between builders and soldiers, every movement shielded by calculated bursts of fire and smoke. Shortly before noon, the bridge neared completion. From above, reconnaissance aircraft photographed a long, dark line extending from the west bank almost to the far shore, the structure glistening against the pale water of the Rhine. The final sections were the most difficult, as the eastern current grew stronger and eddies threatened to spin the free ends away from alignment. To solve this, the engineers used hookers as mobile anchors, positioning them at angles to counter the flow while the last treadway panels were secured. Once the far bank was reached, the eastern anchors were fixed in place, locking the bridge into its final position. The completed structure measured 1,146 feet, roughly 350 meters, the longest treadway bridge ever constructed under combat conditions at that time. It had taken only 9 hours from the first pontoon's launch to the moment the final bolt was tightened. As the smoke began to clear, the surface shimmered with water and oil but stood firm against the river's pressure. The engineers tested it first with jeeps, then with supply trucks, and finally with tanks. Each vehicle moved cautiously, the treadways groaning under the weight but holding steady. By the afternoon, the first columns of the 9th Army were rolling east across the river. Behind them came medical trucks, ambulances, and communication vehicles. The engineers watched as their creation bore the full momentum of the Allied advance, a structure born in noise and chaos, built by hand in freezing water, yet strong enough to carry the weight of war. The Treadway Bridge at Wesel was not merely a product of steel and labor. It was the embodiment of calculation, endurance, and trust, proof that, even in the final storms of war, human ingenuity could master both river and resistance. In the 48 hours that followed its completion, the Wesel Treadway Bridge became one of the busiest arteries of the Allied war effort. From the moment engineers cleared the structure for use, a steady procession of vehicles began to move across its steel surface: jeeps, half-tracks, fuel trucks, artillery tractors, and tanks, each one representing another step in the 9th Army's advance into Germany. The bridge operated continuously, 24 hours a day, without interruption. Searchlights from the western shore illuminated the entry ramps at night, while engineers with flashlights and oil lamps checked joints and anchor lines in the cold darkness. Every few minutes, another vehicle rumbled onto the treadway, its weight sending a shiver through the pontoons before the vibration faded downstream. The statistics were staggering. In less than 2 days, more than 16,000 vehicles and nearly 30,000 troops crossed the Rhine at Wesel. The bridge had been designed for a theoretical capacity far lower than that, but the precision of its construction and the discipline of the crossing columns kept traffic flowing without failure. Military police directed vehicles in strict intervals to prevent overload. Mechanics remained on standby to tighten bolts and replace damaged sections if needed, but no major breakdowns occurred. The engineers' calculations, their careful alignment of anchor chains, their attention to buoyancy and load distribution, had proven flawless under real conditions. The crossing was not merely a matter of logistics. It was a lifeline for every unit involved in Operation Plunder. Armored divisions poured across to expand the bridgehead east of the Rhine. Behind them came supply convoys bringing food, ammunition, and medical equipment. Ambulances carried wounded soldiers back to the western bank, where field hospitals waited among the ruins of Wesel. The same structure that had carried tanks into battle now carried men who had survived it back to safety. Its dual function, forward assault and backward evacuation, transformed it from a tactical bridge into a humanitarian corridor. Civilians also began to appear along the approaches. The fighting had left villages near the river in ruins, and many families, displaced by both German demolition and Allied bombardment, found themselves stranded on the eastern shore. As soon as conditions allowed, engineers coordinated with medical and relief units to use the treadway for evacuation. American medics and military police guided groups of civilians across in convoys of trucks and ambulances. Women and children, some barefoot and carrying bundles of clothing, moved along the narrow walkway beside the vehicle lanes, clutching ropes that served as handrails. To them, the dull clang of the bridge beneath their feet was the sound of escape. For the engineers who had built it, the bridge's endurance was a vindication of every principle they had learned in the field. They watched as each wave of vehicles passed, listening for signs of strain, a change in tone, a misaligned joint, an anchor line beginning to slip. Teams rotated every few hours, working in shifts to inspect bolts, clear debris from the pontoons, and grease the treadways against wear. Despite exhaustion, few men left their posts. They understood that their job did not end with construction, it continued as long as the bridge stood. Every passing convoy was both a test and a victory. Reports from the 17th Armored Engineer Battalion described the conditions with clinical precision: strong current, moderate crosswind, temperature near freezing, no structural failures observed. But in the margins of those reports, officers wrote notes that revealed something deeper: pride, fatigue, and awe at what had been achieved. One after-action summary stated that no orders could have driven the men to such speed. It was their own conviction that the bridge would shorten the war. The success of the Treadway at Wesel resonated far beyond the river. Its performance proved that large-scale crossings could be executed and maintained even under combat conditions. Within days, additional bridges were built upstream and downstream, using the same methods perfected by the 9th Army's engineers. The Rhine, once considered an impenetrable boundary, had become a network of Allied crossings. The Wesel Bridge was the first of them to operate at full capacity, setting the standard for all that followed. When the main combat forces finally pushed east toward the Ruhr, the bridge continued to serve rear units, transporting supplies, fuel, and humanitarian aid. By the time it was dismantled weeks later, it had carried more than 40,000 tons of material across the Rhine. Its story was recorded in the official after-action reports of the U.S. Army Corps of Engineers as a model of speed, efficiency, and endurance. For the men who built it, however, its significance was simpler. It was the bridge that did not fail, a road of steel and determination that connected the last broken edge of Europe to the beginning of peace. The crossing at Wesel quickly entered military history as one of the defining demonstrations of engineering capability during the Second World War. What had begun as a desperate wartime necessity evolved into a technical and organizational model studied for decades afterward. Within days of the operation, the U.S. Army Corps of Engineers compiled detailed reports, sketches, and photographs documenting every aspect of the bridge's design, construction, and maintenance. These records were sent to the Engineer Board at Fort Belvoir, Virginia, where analysts dissected each step of the process, from pontoon deployment under fire to the regulation of vehicle flow. The conclusions drawn from Wesel became foundational to the doctrine of combat bridging in the post-war U.S. Army. The Treadway Bridge at Wesel represented more than a triumph of construction. It demonstrated the synergy of logistics, planning, and adaptability that modern warfare demanded. The crossing had required the coordination of artillery, air cover, transport units, and engineers working with near-industrial precision. This integration of disciplines later became a core principle in NATO military engineering. When the alliance was established in 1949, many of its engineering officers had either served in or studied the Rhine crossings. They carried forward the lessons of Wesel, transforming them into standardized procedures for multinational bridge operations. Post-war manuals on combat engineering, including the widely distributed Field Manual FM 5-277, Bailey Bridge, and its companion texts on floating bridges, directly reference data gathered from the Rhine crossings. In these manuals, the Wesel Treadway was cited as the benchmark for rapid assembly and load capacity under hostile conditions. Charts derived from the operation provided exact formulas for current velocity, pontoon spacing, and anchor tension. These standards were later expanded into the NATO Allied engineering publications, which unified procedures among Western militaries. The influence of those doctrines could still be traced decades later in Cold War-era exercises along the Rhine and the Danube, when NATO engineers practiced large-scale river crossings in anticipation of a Soviet advance. The practical legacy of Wesel extended beyond the military. The techniques refined during the crossing were adapted for civilian disaster relief and infrastructure recovery. The U.S. Army Corps of Engineers, now heavily involved in peacetime reconstruction, applied Treadway and Bailey bridge designs during the massive post-war rebuilding of Europe. Portable modular bridges became essential tools during floods, earthquakes, and other emergencies. The same engineering logic that once carried tanks across the Rhine later carried ambulances across washed-out roads in Germany, France, and the Netherlands. During the Korean War, 1950 to 1953, the principles learned at Wesel were tested again. American engineer units used updated M2 and M3 Treadway bridges to span the Rhine River and numerous mountain streams, often under enemy fire. Reports from Korea emphasized the same methods developed in 1945, decentralized bridge companies working in synchronized rotation, standardized modular components, and the use of amphibious transport to position pontoons. In Vietnam, similar bridging equipment was deployed not for river crossings under fire but to connect isolated bases and flooded terrain during monsoon seasons. The spirit of the Wesel operation, speed, adaptability, and structural precision, survived intact. Even outside the United States, the example set at Wesel influenced a generation of engineers. British and Canadian military schools integrated the Rhine crossings into their curriculum, using photographs and field maps to illustrate planning under stress. The Royal Engineers Museum at Chatham displayed models of the Treadway Bridge alongside those of the Bailey, emphasizing how the combination of floating and modular design represented the peak of wartime ingenuity. In Germany, post-war Bundeswehr engineering units adopted many of the same logistical practices, later producing their own modular floating systems inspired by Allied designs. By the 1960s, the lessons from Wesel had evolved into a global standard for rapid bridge deployment. The NATO Military Engineering Center in Ingolstadt, West Germany, continued to train officers using the Rhine documentation as a case study. Engineers there studied not only the structure itself but also the human elements that made it possible: coordination, endurance, and discipline. They understood that the success of the Wesel Bridge was not simply due to superior materials but to the synchronization of hundreds of individuals working toward a single objective under pressure. Today, the legacy of the Wesel crossing endures in both military and humanitarian contexts. Modern mobile bridges such as the improved Ribbon Bridge and the standard dry support bridge can trace their lineage directly to the Treadway system perfected in 1945. The modular floating concepts, quick assembly pins, and dual-use principles, combat and relief, all originated from the same operation on the Rhine. The engineers who worked at Wesel had no time to think about their future influence. They built to survive and to advance. Yet their bridge became more than a structure. It became a blueprint for how nations could rebuild and respond to crises, linking the art of warfare to the science of reconstruction. The legacy of the Wesel Treadway Bridge endured long after the Rhine had returned to its calm, post-war flow. In the immediate aftermath of the operation, photographers from the U.S. Army's Signal Corps captured the crossing in a series of striking images: dark silhouettes of engineers working knee-deep in the river, columns of vehicles stretching into the fog, and the gleam of wet steel disappearing toward the opposite shore. Those photographs, now preserved in the U.S. National Archives and the U.S. Army Engineer Museum at Fort Leonard Wood, became more than documentation. They became symbols of human ingenuity in the face of chaos, of how engineering could serve as both a weapon of war and a bridge to recovery. In the months following the battle, Wesel was a city in ruin. Nearly 97% of its buildings had been destroyed by Allied bombing prior to the crossing, and the landscape along the river was a wasteland of collapsed walls and twisted iron. Yet it was across the very same bridge that the first convoys of relief supplies began to arrive. Trucks carrying food, medicine, and portable generators crossed from the West Bank, providing immediate aid to the remaining civilians. The engineers who had built the bridge remained on site for weeks afterward, repairing roads, clearing debris, and helping to stabilize the banks against further flooding. To the people of Wesel, the Treadway Bridge was not just a structure built by an occupying army. It was the first sign of reconstruction, the moment when destruction began to reverse itself. As the bridge continued to serve the occupying forces in the early months of 1945, it became a vital supply route for humanitarian operations. Military engineers coordinated with the Red Cross and civil affairs units to distribute food, rebuild water systems, and restore electricity. Photographs from that period show children standing along the riverbank watching convoys cross, their faces illuminated by the headlights of trucks that carried the promise of normal life. Veterans of the 17th Armored Engineer Battalion later recalled that it was one of the few times in the war when their work produced immediate, visible hope rather than destruction. When the bridge was finally dismantled, its materials were salvaged for use in rebuilding local infrastructure. Some of the pontoons were reused as floating docks, while sections of the steel treadway panels were repurposed for temporary roads and construction scaffolding. The operation had left behind not only the technical blueprint for future crossings but also a tangible reminder of what could be achieved when engineering was directed towards survival rather than conquest. In the decades that followed, the story of the Wesel Bridge became part of the broader narrative of the Allied crossing of the Rhine. Museums and memorials across Germany and the United States displayed models, maps, and personal accounts from the engineers who built it. At Fort Leonard Wood, where the U.S. Army Engineer School is located, a permanent exhibit dedicated to the Rhine crossings features the original photographs and field reports from Wesel, alongside the tools, helmets, and equipment used in the operation. Visitors can trace the meticulous notes on load calculations, river surveys, and anchor diagrams, evidence of a generation that combined technical mastery with human endurance. In Wesel itself, the memory of the bridge survived quietly among the city's rebuilt streets. When the town was reconstructed in the late 1940s and 1950s, local historians collected testimonies from residents who had witnessed the crossing. Many recalled the sound of trucks moving through the night, the rhythmic clang of steel plates, and the strange calm that followed the thunder of battle. For them, the bridge marked the first moment when war began to recede. In later commemorations, the city acknowledged the engineers' role not as conquerors but as the bringers of restoration. Over time, the Wesel Treadway came to represent more than a wartime achievement. It became a moral and symbolic landmark. It illustrated how the same knowledge used to wage war could be redirected to heal its consequences. Generations of military engineers studied it not only as an example of efficient design but as a lesson in responsibility, a demonstration that technology, when guided by discipline and purpose, could be an instrument of renewal. Today, the surviving photographs remain haunting in their simplicity, a line of pontoons stretching into fog, men working silently in the cold water, the faint outline of a destroyed city in the background. They captured the paradox of modern warfare, that in the midst of devastation, the human capacity to build endures. For the engineers of the Rhine, the Wesel Bridge was not just a road across a river. It was a road out of darkness, linking the end of destruction to the beginning of recovery. The story of the bridge at Wesel was not merely a technical achievement or a wartime operation. It was a moment when order triumphed over chaos, when the rational discipline of human minds overcame the violence of nature and war. In a world shattered by destruction, the engineers who built that bridge embodied a different kind of courage, one that required precision instead of aggression, endurance instead of rage, and creation instead of conquest. Their work stood as a quiet contradiction to everything the war represented. While others fought to destroy, they fought to connect. In the frozen dawn of March 1945, they proved that civilization itself depended on this ability to measure, calculate, and build even when everything around was collapsing. The Treadway Bridge at Wesel was born in the midst of artillery fire, yet it represented the return of logic and purpose to a landscape consumed by chaos. Every beam, every bolt tightened under the rain was a statement of defiance against disorder. For centuries, the Rhine had divided Europe, empires rose and fell on its banks, armies drowned in its current, and its waters had witnessed the worst ambitions of mankind. But on that day, the river became something else, not a border, but a connection. When German officers later saw the endless stream of Allied convoys crossing the Rhine, they understood that they were witnessing more than a military defeat. What they saw was the triumph of organization, of cooperation, of technical mastery, the very things that total war had tried to destroy. The bridge at Wesel was not built by heroes in the traditional sense, but by craftsmen of stability, whose strength lay in their refusal to surrender to chaos. Their work was a testament to a truth as old as civilization itself, that the ability to build, to impose order upon the unpredictable, is humanity's greatest defense against destruction. The bridge also symbolized the larger transformation that defined the 20th century. Industrial warfare had blurred the line between soldier and worker, between battlefield and factory. Victory no longer belonged solely to those who held rifles, but also to those who held blueprints. The men at Wesel carried no glory of battle, but their calculations decided the pace of armies and the survival of thousands. Their bridge became a reflection of a new kind of strength, the strength of systems, coordination, and intellect. It showed that the modern world would be ruled not by brute force, but by the capacity to organize chaos into something functional, to turn violence into structure. In the years that followed, historians would call the Rhine crossings the last great act of the Allied campaign in Europe. Yet for the engineers who built the bridge, it was not an ending but a beginning, the moment when destruction began to give way to reconstruction. In their hands, steel was no longer an instrument of war but of recovery. Their bridge carried tanks and soldiers across, but it also carried medicine, food, and light to cities that had been starved of all three. The same technology that had fueled the machinery of war was now serving to heal the continent it had devastated. Looking back, the bridge at Wesel represented the moral crossroads of modern history. It showed that progress was not neutral, that engineering, like war, reflected the choices of those who wielded it. In the face of ruin, these men chose to build. Their bridge was more than a structure of metal and bolts. It was a statement about what it meant to be human in the 20th century, to endure, to organize, and to rebuild what had been broken. As the last vehicles crossed and the rumble faded into the distance, the engineers remained on the shore, surrounded by the sound of the river. They had turned one of Europe's oldest frontiers into a path forward. In that silent moment after victory, the true meaning of their work became clear. The war had been about destruction, but their bridge was about continuity, the continuity of thought, craft, and purpose. It stood as proof that even amid the darkest chapters of human history, reason could still prevail over chaos, and humanity could still build its way back from the brink.